And of course we have FEniCS. This is the Shorin solver that Anders and I like to show, because we wrote it in basically 15 minutes, and it's a nice test of how fast you can write it. We also have implemented like G2, various mixed methods, etc. So what we did then was that we tried to we have the input flow here, that's measured by intracranial Doppler, and we also have the outflow here and around there and there, also measured by intracranial Doppler. And we decided that we should only get the input flow, and then we should validate against the output flow once we have calculated it and check that everything was in check. Of course, it failed dramatically. I mean, the measurements were totally different from our simulations. Basically suggesting that we need patient-specific boundary conditions as well that are available with intracranial Doppler. They don't typically use that during their assessment of risk, but they use it after surgery to check whether the patient have any reaction to the surgery. But basically what we found was that instead of using off-the-shelf boundary conditions like resistance boundary conditions, we have to modify the conditions here. So basically the blood is almost sucked out of this part of the brain compared to this part. And it's not unlikely that this is actually happening. I mean, she have developed this condition for a period of many years. So the brain, that side of the brain has probably adapted so that the flow goes more easily into that part of the brain. That's at least reasonable. So by just this might mean something for the ones that know about this. Basically, we have to change the resistance coefficient by a factor of 5. So it's 5 times bigger here than here.
Is this some more resistance, or has it to do with inflow outflow boundary conditions, or what is the resistance?
And typically you put up that it's this is the outflow pressure,
yes,
and it's linear in the flow out. So it gets harder and harder as the flow gets bigger and bigger. So with this coefficient we have to, it's 5 times bigger on the one side compared to the other side.
So it sets the outside pressure?
Yeah, it sets the outside pressure by some. So basically our validation failed. If we are to compute on this kind of problems, we probably need patient-specific boundary conditions. We have also done something similar with canine models that are dog models, where they actually create aneurysms in dogs to check the performance of coils, etc., that they use on humans. So they take a vein and sew it onto the vessel to create an aneurysm. And we have gotten novel MR data, but as you see, I forgot to write anything on here, but this is the flow in various cross-section as measured with MR. And you see that the flow It should be incompressible, so it should be the equal amount through each cross-section, but it's a factor of 20 or something. No, 20% difference at least between the cross-sections. So it's really hard to relate to the real world. Validations, they fail and fail. And there are a lot of uncertainties. This is just an example. This is a mesh we created, or a surface we created earlier. And this is actually what it looks like if you look at the data. And then the surgeons, they come and say that, well, this guy up there, that's a vein, so we have to cut it out. So the eventual geometry is something like that. So I'd say that the anatomy is highly uncertain, and also the velocity measurements. So, to conclude, I think that FEniCS is a fairly good tool for doing patient-specific studies. I mean, we can easily implement new models, etc., in a short amount of time and test new models. And for these problems, new models evidently are needed. We are able to kind of do the whole shebang, go from medical data and to doing simulations. We just need new models, I think. Of course, the accuracy in the input data is a major bottleneck. The input data is very coarse. And we have now a small database of aneurysms and also flow measurements that we can validate against to find the proper models. Questions?